Hello, this is Brooke Cologne for EL6303 for homework 10, question 1, which asks us to collect the definitions of simple properties, of examples of stochastic processes for Poisson process, Poisson increments, Poisson impulses, semi-random telegraph signal, random walk, and Wiener process. As for those definitions, those will be found in the lecture notes, so I will not be going through them here. But as for the last part, which is to explain your understandings of these processes, that is what the answers to 1 through 7 of question 1 will be pertaining to. So for the first one, which is the Poisson process, we have, as for the explanation, it is the mean of the Poisson process is lambda t. Lambda times t, which is a linear function of t. It matches our common sense, which is the longer time we wait for an expected number, the expected number of buses is larger. The autocorrelation function contains the term the minimum of t1 to t2, which comes from the property of independent increments. Then we have the Poisson increment process. Again, you can find the definitions of these within the lecture notes. And as for the explanation of what this means, is that it is introduced to prepare us to define Poisson impulse process, we can see that in the expression of autocorrelation, which is gamma over epsilon minus, lambda over epsilon minus lambda times the absolute value of t1 minus t2 over epsilon squared. And that the absolute value of t1 minus t2 is less than epsilon and is a triangle with area lambda, and it is independent of epsilon. When epsilon goes to 0, the triangle becomes an impulse with the area lambda. For the Poisson implement process, which is defined as z of t is equal to the derivative of x of t, where x of t is the Poisson process. Now, the process of z of t minus lambda has 0 mean in autocorrelation. R of t1 to t2 equals lambda times delta of t1 to t2. That is z of t minus lambda is white noise. And in real world sense, z of t minus lambda is essentially white noise. And again, in the real world, there are some shot noises where there's sort of like impulses. And we may define it as the output of linear time invariant system with the impulse response, say h of t, and an input as an Poisson impulse process. Now for semi-random telegraph signal, we can say that the probability of x of t equaling 1 is not half because we start with plus 1. So the probability of x of t equaling 1 should be higher than a half. And the probability of x of t equaling 1 is equal to e raised to the negative lambda t times the, within parentheses, e to the lambda t plus e to the minus lambda t all over 2, was essentially equals 1 minus e to the negative 2 lambda t over 2. which goes to 1/2 when t goes to infinity, and this is generally what we expect. So the expected value of x of t is equal to e raised to the -2 times lambda t. And it goes to 0 when t goes to infinity. And again, that matches our expectation. R of t1, t2 is equal to e raised to the -2 lambda times the absolute value of t1 minus t2. And that goes to 0, of course, when t1 minus t2 goes to infinity. And this is, again, matching our expectation that when t1 and t2 are excessively far, x of t1 and x of t2 are less correlated. For random telegraph signal, y of t1 is equal to a of x of t. The probability of a is equal to 1, and which is equal to the probability of a equaling -1, and those are both equal to 1/2, where x of t is a semi-random telegraph signal, as we previously discussed. And this just means that the probability of y of t equaling 1 is equal to the probability of y of t equaling -1, which is equal to 1/2. And this makes us guess that y of t may be strict, sense stationary, and the expected value of y of t is equal to a constant. So, excuse me, sorry. Yeah, sorry. So the expected value of y of t is equal to a constant. Next is random walk, which, say, if you toss a coin a number of times, n times, k is the number of heads and n tosses. And again, you can look up the definitions. I won't go into them here because it's rather long. I'd have to make several videos for this. So basically, for a random walk, from probability masses, we can guess that when n goes to infinity, we generally have a Gaussian density. And the autocorrelation function contains the term minimum of t1, t2, and it comes from the property of independent increments. Last is the Wiener process, Brownian motion, and essentially the Wiener process is characterized by certain properties, which is if we say the Wiener process, is W of Wt, sorry, then when W when t equals 0 is equal to 0. And let's say that's the first property. Next property would be that that the Wiener process has independent increments, and it has Gaussian increments, and has continuous paths. Again, if you're having any problems with some of these definitions, again, you can refer to the lecture notes, which the homework essentially does. It's a lot of definitions, and it would be a lot to try to explain in this video, but I'm trying just to get by the understandings of these processes, which is the main point of this exercise, rather than just listing off definitions, which you can find. So if you have any problems, again, just give me a comment on the video, and I'll try to look into it and see what I can find. Thank you.